Guys, so today I want to prove a property of the Noetherian topological space in the algebraic geometry. So basically, let me recall that what is the Noetherian topological space. So there are two very equivalent definitions, but we need the first two. So that any descending chain of the closed subset stabilized. So basically, if you have any descending closed subsets, then there must be n such that they are the same. And then any non-empty collection of closed subset has minimal elements. So basically, if you give me any non-empty collection of closed subsets, and I can find a minimum element. So basically, what it means about the minimum element is that so this is the minimum element, the definition for the maximum and minimum element. So what it means is that there's no any object which is less than m, if m is minimum element in S. Okay, so let me write it down. Is the so if A is the collection of closed subsets, then the minimum means that and the partial, which is partial order, is defined to be the inclusion, not inclusion. The A contains B means the A is containing B means then A is less than or equal to B. M is minimum in A means that if Y is less than S for every S in A, then what? Then Y must be M. And this is called the minimum elements, right? Because there's no any object which can less than if you less than all the object in it, then it must be M. Okay, so this is the definition. This is the definition of minimum elements, and basically you can prove that this one, the 1 and 2, are basically exactly the same. Because if you take any non-empty collection of closed subsets, then you define a partial order, then any chain of it must have minimum elements. Because if the first one is correct, the second one is definitely correct, and then if the second one is correct, then basically then you take any chain and it must be the minimum. It has a minimum elements. Then this is give you the answer. Give you 2 will give you 1. So what I want to prove is the object, in the theory in the algebraic geometry, which says that so there's a definition say that if X is called. So I somehow find this theorem looks stupid, but it basically is tautology. If X is a topological space, okay, and S is so this to X, basically a subset of X. It's called irreducible if X cannot be written as I call it C1 or C2, C1 union C2, which C1 and C2 are closed, and C1 are properly in X, C2 are properly in X, and C1 and C2 are non-empty. So I should say that this is non-empty. Otherwise, there's nothing fun. So if a non-empty closed set X is called irreducible if X cannot be written as 2 proper closed subsets. Okay. And otherwise, X is called reducible. Okay, remember the definition. Then there's a theorem which is really interesting. Say that if X is a Noetherian topological space, then every closed set, I should say non-empty or not non-empty, can be written as finitely union of irreducible closed set. This is a theorem which I think is really interesting because so I didn't tell you guys any kind of somehow deep information. I just somehow like we just do some strange logic. Okay, and the proof is also strange. Okay, so the proof is that I can let A, which become the okay, so I should say suppose not. I can take A basically is the closed set. So C is a closed set. But C cannot be written as finitely union of of irreducible set. So when I define irreducible, I should say irreducible basically must be closed in a definition. Okay. Then that A is a closed set, a collection of closed sets in Noetherian space. So this tell you that there exists a minimum called a minimum object C. C is minimum in A. So there are two cases. The first case, C is irreducible. Then we get a contradiction because we said that C is closed set, which cannot be written as finite union of irreducible set. And then the second is C is reducible. That means that C can be written as C1 union C2, and C1 is proper enough C, and C2 also properly contains in C. But this tell you that the C1 is smaller than C. But C is strictly small, but C is the minimum element in A. So which C1 is not in A. So that means C1 can be written as finite union of irreducible closed set. Also for C2. Then C is union of two irreducible of a lot of finitely union of irreducible set. Then we have a contradiction. So amazingly, this proof looks very strange that it just used the definition of Noetherian space, topological space. Then the definition of the irreducible and the reducible set, and there's nothing important in there is nothing special here. You only need it's somehow like you just play the logic game. So this is why I find this so-called irreducible composition, which is for the Noetherian space, which is really interesting proof. Okay, so I will stop here, and I hope you guys feeling enjoy about this, and I will keep learning algebraic geometry by myself, and I will see you guys in the next video.